The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone, and welcome to the Better Buildings Alliance Space Conditioning Technology Team call. This is Michael Deru from the National Renewable Energy Laboratory, and I think we'll get started now. It's 11:02, so we have a great session today. We're going to talk about some different technology that we have been testing. Here's the agenda. So we're going to do quick introductions with our speakers, go over some updates from the HVAC research team, and we're going to cover three technologies today: infrared air cleaning technology, Grundfos high efficiency circulator pumps, and a Carrier variable speed screw chiller that we're testing. And then we'll wrap up with some discussion and questions at the end. If you do have questions during the call, please type them into the question or chat window, and then we'll answer them at the end. And if we have problems there, we may be able to unmute you and have you speak directly on the call. So the speakers today, this is Michael Deru. I'm a senior research engineer at the National Renewable Energy Laboratory. I lead the Better Buildings HVAC research team and the Advanced Rooftop Unit campaign, and I work in our Building Energy Science group at NREL. And we also have Jesse Dean, who's been at NREL for about 11 years and leads manages our testing with the GSA Proving Grounds and the Department of Defense ESTCP program. And so I'll be filling in for Oak Ridge today. Oak Ridge National Laboratory did the testing on the Carrier variable speed screw chiller. Unfortunately, they were unable to join the call today, but I will be filling in for that presentation. So just some quick updates on the HVAC research team. There were several great presentations and sessions at the Energy Exchange and Better Buildings Summit. If you were unable to attend, or if you were able to attend but couldn't get to all the sessions, all the presentations are available now. You can go to this link and download those presentations. We have several reports coming out this year. High efficiency motors for refrigeration condenser fans, an RTU AFDD landscaping study report. We'll talk about this infrared gaseous air cleaning technology. There's several reports on cooling tower water treatment technologies that will be coming out through GSA Proving Grounds and DOE testing. High efficiency circulator pumps, actually that is we're going to talk about today also, and that report was just published yesterday. And then some new and ongoing projects. We're going to ongoing with the RTU AFDD, and this year we're going to focus on collecting actual performance data from rooftop units. So that'll be exciting. And if you have projects and you'd like to share information, please let me know. And then we're also going to be starting up RTU coordination. So what that means is coordinating the control of rooftop units on a single roof. So instead of individual control, you'll control them kind of as a system so that you can manage energy and demand performance of those rooftop units. And as always, please check out the HVAC resource map for any of this information, especially this is mainly focused around central plants, so large chilled water and hot water plants. Some great resources there. All right, so let's get started here on this infrared air cleaning technology. But before, I just want to give a background on ventilation and indoor air quality, so we can have a good starting point. It's always a balance in a building to maintain good indoor air quality and energy consumption, because we have to oftentimes bring in more outside air to improve indoor air quality, and ASHRAE standard 62.1 sets the ventilation rates for indoor air quality. And so typically that's done with dilution. So we bring in more outside air and dilute the pollutants that are inside. So that assumes that your pollutants are inside, right, not outside. We can filter outside air. Typically we do for particulates, but that's about all we filter out of the outside air. So 62.1 has a ventilation rate procedure where they specify ventilation rates by different building activity for area and the number of occupants. You can also, so that's kind of the default method. If you don't do anything else, you should follow the ventilation rate procedure. You can also follow the IAQ procedure or IAQP, and that allows you to set the ventilation based on controlling your identified contaminants of concern. And you have to prove that through, you have to identify the contaminants of concern and then show through mass balance equations that you are maintaining those under the limits that are specified by your authority having jurisdiction. And that may actually raise or lower the ventilation rate depending on what your sources of pollution are. All right, so the technology that we're going to discuss today was developed by Inverid, and they licensed this solid sorbent technology from the National Energy Technology Laboratory, or NETL, and it absorbs CO2 from the air. And then they developed their own formulation that removes volatile organic compounds, including formaldehyde and aldehyde and so on. The advantage of this particular sorbent material is that it has a low regeneration temperature between 130 and 150 degrees Fahrenheit, and it's unaffected by humidity levels. So other sorbent materials have very high regeneration temperatures, and humidity tends to reduce the effectiveness of the material. So in this case, the advantage is that it does have that low regeneration temperature and unaffected by humidity. So what they've done is they take that sorbent material and they put it in these cartridges, and then they put it into this device they call the HVAC load reduction or HLR module. And you can see a picture of it, of one of the versions here. And you have process air coming in, it goes through those sorbent cartridges, removes the gaseous contaminants, and then it's the process air is then delivered to the building. And then during regeneration mode, those dampers are closed off, and the regeneration air, you bring that in. Well, actually, first what they do is they heat up the sorbent cartridges to release the gaseous contaminants, and then they flush it out through this regen air in an outlet and flush that to the exterior outside of the building. All right, so typically what you would do is you would install this in two places, either in the return air duct, as shown in that bottom right-hand picture. And so you treat about 10% of that return air, remove the gaseous contaminants, and then deliver that to the return air duct and then to the building spaces. Or you could put this into direct, like if you have a large return air plenum, you would just put that HLR right in the return air plenum and treat the air right in the plenum itself. And then, as I said, during the adsorption cycle, it removes the CO2 and VOCs. And then once or twice a day, depending on the level of pollutants and the number of hours of operation, you have to go through a regeneration cycle, and which takes about 30 minutes, but it can vary depending on how long or how many contaminants that you want to purge. And you do that maybe at night time or during period of low occupancy. And then when the HLR is on and you can clean out the inside air, then that allows you to reduce your outside air in the building, and which leads you to energy savings, because now you don't have to treat that air to condition that air, to either cool it down or heat it up depending on the time of year. All right, so we did our test site criteria when we were looking at buildings. The biggest challenge is understanding what the OA flow rates really are in the building, and that you can maintain, what is the air balance with the exhaust and air and the outside air ventilation are coming into the building. And you have to have enough air enough OA that you can reduce in the building to actually save energy. Here's a couple pictures of outside air dampers. The top one there obviously is rusted and stuck shut, so that had to be replaced before this technology could be installed. And so the dampers have to be operable, and they have to be controlled by the HLRs. Hopefully there's no existing ventilation or IAQ problems in the building, or if they are, we'll have to evaluate those. In some cases, the HLR can actually relieve some of those IAQ problems, depending on what it is. Obviously, you need to be able to install this, so you need space and access to the return air ducts if you're doing that. And you have to have enough hours of operation and the climate to really give you the energy savings that you're looking for. We'll talk more about that. So we looked at multiple sites, and all is a retrofit opportunity. So we ended up deploying this at 6 different sites. We were able to collect performance data at 2 sites. One site had capacity challenges that unfortunately we couldn't establish a baseline, but we were able to show significant improvement in overall performance of the building. So we'll talk about that as well. And then 3 sites we had ventilation system problems or other mechanical problems, and we couldn't actually show energy savings. So we'll talk about those a little bit, but basically that was a learning process in this whole system. All right, so the first site that we installed at was the University of Miami Health Center. It's their fitness and wellness center. It's a 60,000 square foot building. It has a variety of spaces. Some, as you can see, there's a workout fitness room. There was some office space and some common areas and some meeting rooms and so on. They installed 3 HLRs in the return air duct path. There's a picture of one of them installed there. And then we collected data during the summers of 2015, 2016, and 2017. And what we did is we did week on, week off operation. So we could have the 2 on-off baseline and then the invariant HLR operation to determine performance. Unfortunately, there were several challenges with damper operation, and a lot of that was due to facility staff not understanding that we were conducting these tests, and there were some other challenges with stuck dampers and so on, but we were able to get performance data, just not as much as we wanted. All right, so second building was the Morgan Stanley headquarters building in New York City. This is right on Times Square. It's a 42-story, 1.3 million square foot Class A office building. So obviously a very large building, very different than the other building. This one, they were able to put the HLRs in the return air plenums. So there's 40 units in this building, 20 on the 7th floor and 20 on the 28th floor. And then we were able to collect performance data during the 2017 summer. And then we had some, unfortunately, we were unable to monitor this during the winter time to get heating season operation because there were some exhaust challenges. Those have since been corrected, but we did not get winter time operation for the 2017-2018 winter. All right. And then the last building was the ArcBest headquarters in Fort Smith, Arkansas. This is a 190,000 square foot, 5-story office building. The occupancy in this building was about between 17 and 20% over the design, which meant that the existing chiller plant and air handling units were undersized for that occupancy, and they were unable to actually meet the conditioning and indoor air quality requirements. And they were looking at options of upgrading their chiller plant and air handling units or installing HLRs, and they were able to meet their requirements with the HLR operation. So we'll talk about that as well. All right, so the Wellness Center at the University of Miami. It's interesting because the first year in 2015, we saw about a 10% chill water savings, but unfortunately, one of the dampers on one of the HLRs was stuck open, which drastically reduced our energy savings. The next summer, we had some good data for about a month period, and we saw 28% chilled water savings. And then the last summer, 2017, we saw almost 37% chilled water energy savings. So very good performance here. Obviously, but there was some uncertainty in the 08 damper position again, because we couldn't see remotely where the dampers, what the position was, but we saw very good performance. Indoor air quality, we had to show that we were maintaining that. So we identified from these contaminants of concern and did some testing during the 2015 summer at multiple locations in the building. So everything passed except there were 2 locations. The formaldehyde was slightly over the performance criteria, which there was it was considered to be overall a pass because this building at the same time had at the time of the testing in 2015 there was a food service in this building, which was removed after that season, and it's unclear exactly what the source of the formaldehyde was, if it was furniture or from the food service. But anyway, I think they were going to do additional testing and didn't do that. But overall, we considered this to be a pass for the testing. The Morgan Stanley building, we saw, unfortunately, we were able to get, we only got data for about a 2-month period there, and the conditions were highly variable. In other words, the outdoor air conditioning, the temperature was highly variable from day to day. Some days were better than others. Some days were hot. Some days were actually cool. If you have a cool day, you have lower energy savings overall. But we saw about a 4.6% chilled water energy savings, which may not sound like a lot, but actually this because it's a large building, the chilled water it's a very high cooling load, and it's really dominated by the high internal loads because it's a high occupancy building with a lot of computers and other internal loads and plug loads. And then this is a large glass high-rise building in New York City, has very high envelope loads as well. So those are really the dominating factors for chilled water for a cooling load in this building compared to the outside air load in the building. and it did pass all of the indoor air quality. They did pretty extensive testing by 2 parties, tested the building, and everything looked very clean. The interesting thing here too is that the last 3 contaminants there, ozone, PM, particulate matter 2.5 and 10, are really outdoor sources. And this building, because it's in New York City, can have some problems with ozone and particulate matter if bringing in a lot of outdoor air. So reducing the outdoor air can actually improve the indoor air quality from those sources. And that's true of other locations with poor outdoor air quality. This technology can help significantly. All right, the ArcBest headquarters, as I said, they were over occupied in the building compared to the design. So we couldn't establish a baseline because we couldn't meet the ventilation and IAQ requirements with the existing system. But with the HLR operation, the building was able to meet the IAQ and thermal comfort requirements, and they avoided a costly upgrade to the chilled water plant and the air handling units. So the building owner was, and they had, as I said, the temperature and RH improved, so the occupants were very happy, which makes the owner very happy with the building, and they were able to save a lot of money on chilled water plant upgrade. So this was a pretty big win for the building owner. And then they were able to show energy and water savings for the annual, on an annual basis. And also, because they're reducing the amount of outside air intake to the building, they extend the life of the filters in the air handling units. So that's another win, I guess, from the building owner's perspective. So this technology, it works. Well, it removes the CO2 and VOCs and allows you to reduce the outside air. However, the energy savings are going to be highly dependent on, how much you can reduce that outside air, the hours of operation, your climate that you're in. Obviously, it's best if you can have a long cooling season, hot, humid, especially is good climate for this technology, and a long heating season, or a mix of cooling and heating climates like New York City or Chicago, where you have both high cooling and high heating loads. And it works well if you're in a location with poor outdoor air quality, because now you can reduce the amount of outdoor air that you're bringing into the building. If you're looking at a retrofit, you really need to know the outdoor airflow rates and the air balance in the buildings. And this was the biggest challenge we found in this whole demonstration, was finding a building that we had confidence in the outdoor airflow rates. And we recommend doing, if you haven't done a measurement of your out and a balance, testing air and adjusting a balance of your system, recommend doing that before you install this system if it's a retrofit. In new construction, now you have the opportunity to design this into your system and design the space for it and your ventilation airflow rates and everything. And potentially you may be able to reduce your HVAC system and actually reduce your overall HVAC costs, because now your load is reduced because your outside air ventilation requirements are reduced. All right, so let's move on. And Jesse Dean's going to talk about high performance circulator pump testing that we did.
Yeah. Hey, good morning, everyone. This is Jesse Dean with NREL. So I currently manage the support we provide for the GSA Green Proving Ground, and then also for the ESDCP program. And then today I'm going to talk through the results for a high performance circulator pump demonstration that we conducted. You'll see on the screen here, we did just recently publish the report, and so it's available for download through the NREL website. And then GSA is currently working on the 4-page findings document and infographic, which will be available in a couple of days here. And then also we have a webinar for this product that's coming up on October 11th. If you haven't attended these webinars, I would encourage you to kind of attend one. You get to hear from, the GPG program director, and then also from the GSA site staff, which I think is really helpful in just kind of understanding, the facility operators' interaction with the technologies. So just a quick introduction to high-performance circulator pumps. So a circulator pump is essentially a small pump that has the motor rotor, the pump impeller, and the support bearings that are all sealed inside of the pump. Sometimes these are called inline pumps, as those pump flanges that you'll see there are kind of directly mounted in line with the piping system. Normally for circulator pumps, these are constant volume. The older ones use a inefficient induction motor. So here you can see these are applied to pumps that are about 2.5 horsepower or smaller. The primary application of them are domestic hot water recirculation pumps. You'll also see a lot of them for air handling unit booster pumps, for either heating system, for the air handling unit heating coil or the cooling coil, or for kind of radiant baseboard heating. So these are kind of the smaller circulator pumps that serve miscellaneous loads within your facilities. I think one thing to note here is that the Energy Policy Act of 1992, which kind of set some of the first motor efficiency standards in the U.S., only goes down to 1 horsepower. So a lot of times when you're looking at these really small pumps, they tend to have much lower kind of motor efficiencies and power factors than some of the larger induction motors. And really the technology innovation here comes from moving from an induction motor to an ECM motor. It does have kind of integrated variable speed control, and so you don't have to have a secondary variable frequency drive. These ones that we monitored also have a number of kind of built-in control modes and onboard monitoring in them. And so essentially it's kind of like a integrated pump with integrated sequences of operation, integrated metering systems that are all within the pump. And so you can see we have a number of different control modes that can be operated within the pump. The way to kind of think through these control modes is for a typical domestic hot water recirculation application. Normally you're just going to be going with that 4th one down, the constant temperature. And so essentially the pump has an internal temperature sensor within the pump. You typically set the domestic hot water return temperature to a set point within the pump to about 10 degrees below your domestic hot water tank set point. And so essentially the pump kind of ramps up and down to meet that return water temperature set point. When you're working on HVAC systems, some of the common applications of these are kind of the auto adapt, or there's a differential temperature mode. The one that we ended up using is just a standard kind of 0 to 10 volt control mode that comes off of the air handling unit and is essentially kind of setting the pump speed based on whatever flow rate is needed for discharge air temperature set point. So just a quick comparison to other pumps, you'll see these kind of high performance circulator pumps have about a 10 to 15% improvement in hydraulic efficiency. So the pumps themselves are more efficient than other circulator pumps. 10 to 20% improvement in the electric efficiency from the ECM motor. And then really the large savings comes from the ability to kind of ramp the motor up and down to meet the load rather than running it at a constant speed. The one that we looked at, does have an integrated nighttime setback that can be programmed in there, but really the large savings comes from that variable speed operation on these. And currently about 90% of the circulator pumps in the US are kind of the standard induction motor ones. So there is a very large opportunity in the United States with over 30 million of these small circulator pumps that could be upgraded. So the ones that we tested for this GSA project were actually the two smallest pumps that are manufactured by this particular manufacturer. So you can see on this graph, they offer a number of different kind of models for this particular pump. And so, for example, in certain applications where you have really large flow rates but relatively low head pressure, you can get up to over 300 gallons per minute. When you're looking at things like domestic hot water recirculation pumps, normally what's happening is you're going to have really high head pressure because you're having to pump that fluid up to the top of the building and then back down with relatively low flow rates. And so, you know, where we were kind of operating with these systems is over on the left-hand side where the 32100 is showing up, where you have kind of high, you know, head pressure and then low flow rates. One thing to note too is when we started the demo, the smallest pump they made was the 4080. And then about halfway through, they started selling the 32100. So we kind of tested two different versions of this pump here. So the first test case that we looked at was a domestic hot water recirculation system. So this was installed on a 14-floor office building in Lakewood, Colorado. The domestic hot water loop number 1 essentially kind of served the first floor. And so it was serving kind of a cafeteria on first floor of the building. The domestic hot water pump number 2, that second table there, is serving floors 2 through 8 of the building. And again, they're set up as a domestic hot water recirc to provide hot water to the domestic hot water loads on those floors. And then essentially we have a quarter horsepower baseline pump for the first one. We have a half horsepower pump for the second one, and the model 4080 doesn't directly correlate to the same horsepower ratings, but you know, it's around a 0.37 horsepower, but was still oversized for the load. And then again, about halfway through the demonstration, we installed this 32100, which is a quarter horsepower pump. And I think one of the challenges in sizing these small pumps is you don't have kind of differential pressure ports on the pumps themselves. So it's hard to know exactly what the flow rate is through the system. We do go through in the report kind of a methodology to help analyze if the flow rates are appropriate and if you can install a smaller pump. But just one thing to keep in mind, it is challenging with these smaller pumps of really knowing, you know, what the flow rates are. So just really quick going through the duty point power numbers, you'll see that for both of these, we had very significant reductions in power draw. So the duty point power is essentially, you know, how much power is the pump drawing at the peak kind of flow rate and differential pressure that the system sees. And so for the domestic hot water pump number 1, we saw about a 44% reduction in peak power with the first one, and then with the second one, it was about 72%. So even if these pumps would have just ran at 100% speed, you're still getting on the order of kind of 72 to 44% energy savings there. So, you know, essentially it's kind of showing these are way more efficient than the current pumps. You do see that with the wire to water efficiency numbers. Wire to water efficiency is essentially the pump efficiency multiplied by the motor efficiency. And when you're operating in scenarios with, you know, high differential pressure and low flow rates, you're running on a very challenging point of the pump curve. And so normally you do have kind of lower wire to water efficiencies than on kind of larger central plant pumps, for example. But you'll see on the first one, we did improve from 8.2% all the way up to 30%. The domestic hot water pump number 2 had about double the flow rate of the smaller domestic hot water pump number 1. And so you'll see it was able to operate at an even higher kind of wire-to-water efficiency there. But I think the main takeaway on this is we saw, very significant reductions in pump power at the peak load for those pumps. So this graphic just kind of shows the daily average load profile for each system. So over the monitoring period, we essentially just kind of averaged out what the pump hour was at each time step. And you can see for a constant volume pump, it stays very, very constant. And so this is one of the big issues with constant volume pumps and also constant volume fans, is essentially there's no reduction in pump power or fan power based on the load that the system is serving. And then with the newer pumps, essentially what you'll see happening is, they kind of spike in the morning when the system is turning on to try to warm up that domestic hot water loop. And then kind of just fluctuate a little bit throughout the day. But as you can see with the domestic hot water recirc system, essentially what happens is you're able to run at a very low pump speed until people are actually turning on faucets and using domestic hot water. And so you have very significant savings on the system. So just really quickly on the energy savings. So for domestic hot water pump number 1, we saw about 90 to 96% energy savings. Domestic hot water pump number 2 was again 94 to 96% energy savings. And just to kind of reiterate, some of the reasons the savings were so high was because, these are the smallest pumps that are manufactured, and they're operating at a very challenging point on that pump curve. So when you can provide a pump that is a more efficient pump, operates at a better point on the curve, you do get very substantial savings. I would say that this is probably not going to be representative of all domestic hot water recirc systems, but in this case, we did get really good savings on that one. So this just kind of walks through the energy savings and economics here. The site did have kind of a time of use rate structure, and so we have, energy cost savings, demand reduction, and all of those things that are listed in here. The big driver for savings on this, though, was actually the O&M cost reduction. So you do not require kind of greasing of bearings or have to replace pump seals on these. And so the on-site GSA staff estimated about $75 per year for O&M, and you can see it resulted in kind of good economics across the board here. So the second application that we looked at is using it in a heating hot water circulator pump. In this case, we did a side-by-side testing. So rather than kind of doing before and after testing on the same system, we essentially just tried to find 2 air handling units that were roughly equivalent and used one of them as a baseline and then the other one as the test case. For these, they're kind of air handling unit booster pumps. You can see the way that they're configured is you essentially have a 3-way control valve that diverts water around the heating coil when that valve starts to close off. So again, when these units turn on, the pump power stays constant throughout the operational period. So for the Magna 3, we essentially just installed a bypass valve, closed the 3-way, or converted this to a 3-way to 2-way valve, and then allowed it for automated flow control with the pump itself. So the air handling unit numbers definitely gave us some problems. One of the issues that we had was A217, actually its pump had failed prior to the demo. And so we did have to install kind of a brand new pump from Grundfos that was considered a market standard pump, but it was not kind of an older, 10 or 15-year-old pump. And you'll see kind of the impacts of that. Another big issue that we had was when we originally selected the building, the pumps had very long run times in the heating season. but we found that they were not meeting the discharge air temperature set point and were essentially, not meeting the load requirements. And so we had to kind of put the project on pause, retro commission the whole facility, and then come back and do the demo. And when we did that, the AHU 19 was essentially serving an internal zone within a building and would only run for like a couple hours in the morning to preheat the zone, switch over to cooling mode, and then run for a couple more hours in the afternoon. So definitely ran into some more issues on the heating one here. So the energy savings that we got out of this one are substantially lower than the other one. I think the primary driver for that is if you look at AHU 17 versus 19, the max power, essentially the new kind of market standard pump by this manufacturer is much more efficient than an older pump that would be sitting in there operating from 10 or 15 years ago. And so instead of seeing, a 40 to 70% reduction in peak power, we're only seeing about a 7% improvement. So really the energy savings come from that variable speed operation. And given the fact that these pumps only turn on for about 4 or 5 hours a day, they were running at a higher, percent load throughout the day. But overall, we did see about a 25.7% improvement in energy savings. And again, on this, just with the O&M savings alone, it's enough to kind of justify the economics of the system. We did run a couple of other scenarios where we were trying to match the runtime of AHU 19 to AHU 17, which was running about 20 hours a day. And we do think if you did have kind of a 10 to 15-year-old pump in there, you still would see very substantial peak power savings in that case. So some of the recommendations here is essentially, deploying these as end-of-life replacements. We did look at the installed cost as the delta between a standard pump and this high-performance circulator pump. I think for all the facility managers, though, first step is to target your domestic hot water recirculation pumps. We found even with very low electric rates and 40 hours a week of operation, they should be cost effective. For heating hot water and chilled water pumps, you want to make sure that you're selecting pumps that have sufficient runtime. So we're targeting, 10 to 12 hours a day, roughly 8 months a year. Something else I think to keep in mind with these is a lot of times, like with radiant heating coils or even with air handlers, you might have one pump that serves multiple coils instead of the case that we had where it's, one pump per one coil. In those cases, you should have better economics because those are operating continuously throughout the day. And you'll have a greater degree of variation in your load. So kind of look for those radiant baseboard heating opportunities. And then also with ground source heat pumps, they're operating in heating and cooling mode throughout the year. So if you do have kind of smaller ground source heat pump systems, these pumps could be applied to either the ground loop or the building loop in that case.
All right. Great. Thank you, Jesse. So now I'm going to present on these high efficiency chillers for Dan Howitt from Oak Ridge National Laboratory. Actually performed this project and since retired. So I'll be presenting for him. So what happened, this was another GSA Proving Ground project at the Sidney R. Yates building in Washington, D.C. This is a historic building. It's currently the headquarters for the U.S. Forest Service. You can see, it's a beautiful building, and it went through a major renovation in 2013 to kind of make it into a modern office building. And then these chillers, they were replacing, it had 2 chillers. They replaced them, and it was a good opportunity for this test, and we tests were performed during the summer of 2016. So the two chillers that were installed in this building, one, the variable speed direct drive screw chiller from Carrier, and then also variable speed direct drive magnetic bearing chiller, which is a chiller that has been on the market for quite a while, and several GSA has several of these in their buildings, but they wanted to test that against this variable speed screw chiller. So both chillers operate in parallel in the same chill water loop, same pumps and everything, and so they were able to alternate performance on one day one chiller and the next day the other chiller, and collect data throughout the summer of 2016. So here's what we have, the two chillers. One was a 275-ton chiller, the variable speed screw chiller. The magnetic bearing chiller was actually a 400-ton two compressor chiller. So it's not a perfect direct comparison, but it's very close. And then you can see the cost, and the cost per ton of the two chillers is relatively similar. And that cost, obviously, if you've ever purchased HVAC equipment, you're going to get a different cost every time you go out and compare. So you're going to have to cost that for your own project, and you'll probably get a different price. If we look at the rated performance of the two chillers, they're nearly identical. The IPLV is identical for both chillers, and it's significantly lower than the FEMP standard for chillers. So there's about a 35% improvement over the FEMP. FEMP is the Federal Energy Management Program standard for chillers. So, and that's already a good chiller. So these are both very high performance chillers. So they did two methods of estimating performance. One was a cooling rate, trying to estimate the cooling rate in kilowatts per ton. So they collected the chiller KW, outside air temperature, condenser water temperatures, and then they were able to estimate the chilled water flow rate through basically a differential pressure measurement across the condenser, and then looking at the pressure curves provided by the manufacturers. But that gives you a pretty high uncertainty in that flow rate. So then the second method was just looking at energy, chiller energy as a function of outdoor air temperature. And further, they bin that data by the outside air temperature and the condenser entering water temperature, because each chiller actually has a different performance, different entering water temperatures. So when we look at these two methods, the variable speed screw chiller had the lowest energy performance. By method 2, estimated about 4% lower. Method 1, about 11% lower. So there's a range, and you're going to get, depending on the application, you're going to get different performance too, depending on how many hours, the different loads that you're operating in. So in conclusion, I mean, both chillers performed very well. As I said earlier, they're about 35% lower than the Federal Energy Management Program standard for water-cooled chillers. Both chillers provided excellent service to the building and chilled water supply temperature. They both had similar maintenance, basically no maintenance challenges during the demonstration period. And there were, the operations personnel liked both chillers. They both worked well. One kind of significant difference between the two is that the variable speed screw chiller is very has a wide range of condenser water entering temperature, so it can go from a low temperature up to a high temperature, whereas the magnetic bearing chiller can also do that, but you basically have to, it has to be special ordered for your operating conditions. So it's kind of custom built for, or custom ordered for your operating conditions, whereas the variable speed screw chiller can just accept those lower and high entering water temperatures. Overall, GSA recommends that, you know, both chillers are good chillers, and you know, consider both when purchasing a new chiller as either a new construction or as a retrofit. So look at both. That's basically your conclusion. There, as with the other circulating pump projects, GSA has several resources available. There's a technical report. There's a 4-page finding. If you don't want to read the whole technical report, you can get kind of the highlights in that 4-page finding. If you really don't even want to read that, you can go to the infographic and get the 30-second or 1-minute kind of overview. All of those, and there's a webinar, again, that they did on January 2018. You can go and look at, review, view that webinar and view the slides. And in that webinar, as Jesse said earlier, you get to hear from the people who perform the M&V, but also from the building operators. So you can see, you get to hear what their experiences with these different technologies. So you can go to that website there. We will take this webinar, will be recorded, and you can listen to it later, and we'll make these the slides available to everybody, so you don't have to write this down. You can get those. All right, so I do have one question here. Actually, I'm going to go to the next slide. If you do have questions, please type them into the question window, or you can email myself or Jesse as well after at any time. And we had one question: did we do a life cycle analysis of the two chillers? So I don't believe they did a life cycle analysis. They did do a simple, you know, payback analysis and but let me see if I can find it. I don't have that in my, off the top of my head. But let me see if there, and again, if you have any other questions, please type them into the window there. Another question was, were any modeling efforts performed to determine how well these technologies would perform for other candidate buildings in terms of energy savings? So for the first one, for the infrared air cleaning technology, we are in the process of doing some of that energy modeling to look at especially different climates, and looking at the energy savings across the U.S. in different climates. And then the performance will also vary significantly on how much air you can reduce. So that will be included in the final report. I think for the circulator pumps, I don't think there was any attempt to do buildings or modeling in other buildings. I think the chiller performance, again, we didn't do modeling for other buildings because it's really going to depend on your chill water load. If you know what that load looks like, and especially if you know what it looks like across the year, you should be able to calculate that. One other question: did the automated control functionality of the Grundfos pumps contribute to savings or improved operations? Are there other small circulator pumps with ECM motors?
Mm-hmm. Yeah, so that's a good question. I think one of our primary findings was it is very valuable to have the pre-programmed sequences of control sequences that are inside of the pump. Essentially what you run into is with these very small pumps, if you are integrating these into your building automation system, you know, every point that you add is actually more expensive than the pump itself there. And so, you know, having the ability to, you know, pick a control mode within the pump and then use kind of the standard on-off within the building automation system is definitely a benefit. And so the more kind of points that you need to add, you know, to the building automation system just increases that price. So in our report, our general recommendation is to integrate the fewest number of BAS points per pump as possible. In terms of the other manufacturers, I would say that, you know, there's definitely other manufacturers that I know for sure at least provide the ECM circulator pump with the internal temperature sensor to do the constant return water temperature for the domestic hot water recirculation pump installations. I'm not sure, you know, how many other ones have kind of the full suite of internal controls for heating applications.
And that whole question got cut off, but the question is, can the other ECM motors reduce O&M costs?
Yeah, so the O&M cost, I think, is a good question. For the, you know, estimated 30 million of the older induction motor-based pumps, I would anticipate that that O&M cost is valid for all of those. If you already have kind of a more modern circulator pump, you know, we haven't looked into the O&M cost savings for that one.
And one last question here for the circulator pumps. Were there any observations on reductions in water hammer? Basically, could the rate of change of the speed of the pump to maintain differential pressure accommodate huge fluctuations in demand without pressure spikes leading to the water hammer?
Yeah, we didn't have any observed kind of water hammering that was going on from the building operations staff. That is a good question, though. It was not something that was observed during our demonstration, though.
All right, I think that's all the questions, and we're at the end of our hour. So thank you, everyone. Please, again, if you have questions, feel free to email either myself or Jesse. And as again, we will make this webinar and presentation available to everyone. So thank you, everyone, and have an enjoyable rest of your day.